Good morning. My name is Prathamesh Jadhav, and today I'll be presenting on the topic circular dichroism spectroscopy, which is a vital analytical technique for studying chiral molecules. Now, this presentation is part of our analytical technique course, and I look forward to discussing this fascinating subject with you. So, let's begin with a basic understanding of circular dichroism or CD spectroscopy. It is a technique that measures the difference in the absorption of left and right circularly polarized light by chiral molecules. This differential absorption provides insights into the structure and behavior of biomolecules, particularly proteins and nucleic acids, which includes DNA, RNA. CD spectroscopy is crucial in understanding how biomolecules function and interact. Now we can see very new words pop up here, such as what is polarized light, what is circularly and left circularly polarized light, what is chiral molecules, what is differential absorption. We'll have a look at it in the next slides. Let's have a historical background. CD spectroscopy has its roots in the early 19th century when Jean-Baptiste Biot discovered optical activity. Later, advances in instrumentation led to the development of the first CD spectrometers in 1960s. Now, today it is widely used in structural biology and pharmaceutical research. Yes, about those terms now. What is chirality? Chirality is the property of a molecule of being non-superimposable on its mirror image, much like our left and right hands. The thing about mirror images of any objects, like we can see in example of our left and right hand, if we put our left hand on top of our right hand, we can see that the fingers and the shapes do not match. The odd pairs include the little finger and thumbs of both hands, and the only even pair or the matching pair is the middle finger on top of each other. Other than that, the our hands are chiral, that is, they are non-superimposable. The next thing is that these chiral molecules, they interact with light differently, leading to optical activity. Now, optical activity, it refers to the interaction of light with chiral molecules, which causes rotation of the polarized light. CD spectroscopy exploits this property to study chiral molecules. The principle of circular dichroism, it lies in interaction of circularly polarized light with chiral molecules. Left and right circularly polarized light are absorbed differently by these molecules. This resulting difference in absorption is called as ellipticity, and that is what we measure in CD spectroscopy. This ellipticity is unique for each molecule. Then there are types of circular dichroism. There are two main types of CD spectroscopy. First is electronic CD. It focuses on absorption in the UV visible range, which is particularly useful for studying proteins and DNA. Second is the vibrational CD, which operates in the infrared range and is used for smaller chiral molecules. Each type serves unique applications. Next is the light polarization in CD. Now, what exactly is polarization? What is planar light and all of these? We'll understand here. Now, to understand this CD spectroscopy, we need to grasp the concept of polarized light. Linear polarization involves light waves that are oscillating in a single plane, whereas circular polarization involves waves that are rotating in a helical pattern. We know helical pattern as the structure of DNA. It is double helical pattern. So something like that. Now, CD spectroscopy, it measures the difference in absorption between left and right circular polarization. And it is because in CD, the circular polarization is essential as it interacts differently with chiral molecules, and then it gives us a measurable signal. So let's have the instrumentation overview. The main component of CD spectrometer, it includes a light source, a polarizer, a modulator, a sample holder, and a detector. The light source, it generates the spectrum, which is polarized and modulated to produce the circular polarization. The detector measures the differential absorption of light by the sample. This is the schematic diagram of our the CD spectroscope. See in detail. First is the light source. Now there are two widely used light sources here. First is xenon arc lamps and second are deuterium lamps. Xenon arc lamps, they are a common source for UV visible CD spectroscopy and they produce a broad spectrum. Second ones are deuterium lamps, which are another source for UV visible CD spectroscopy and they're ideal for far UV region. These provide a continuous spectrum of light in both the UV as well as visible range of the light. Next instrument is polarizer and modulator. So the polarizer, it ensures that only polarized light enters the system, and modulator, it creates alternating left and right circular polarization, allowing for differential absorption measurements. Next is the spectrometer itself. The first is in it we are studying the sample holder now. Sample holder, they are typically made of quartz and they are quartz cuvettes and they are used to hold the sample, ensuring that there is minimal interference with the light beam. Cuvettes come in various sizes and they can be temperature controlled for accurate measurements. As for detectors, the photomultiplier tube is the heart of the detector. It measures the intensity of absorbed light and it computes the electricity. Now, this sensitive device, it amplifies the light signal and allows for detection of even small differences in absorbance between left and right circular polarized light. Now, this is how you represent data. CD data is typically it is represented as a plot of molar electricity. This part on the y-axis versus wavelength on the x-axis. Now, peaks in the spectrum, they indicate specific structural features such as alpha helices and beta sheets in protein. As we can see here at 208 nanometer and 218 nanometers, we are getting negative peaks, strong negative peaks. And at 195 nanometer, we are getting a strong positive peak. So these are used to represent the interactions of chiral molecules with the light. Next thing is their applications. Now, first is protein analysis. Now, CD is widely used to study protein folding, stability, and interaction with ligands. It can also be used to analyze protein-protein interactions and to monitor changes in protein conformation upon environmental changes. For example, as we saw in alpha helix, the exhibit characteristic negative peaks at 208 and 222 nanometer or 218 nanometers. Next is DNA and RNA analysis. They are called as nucleic acids, and CD helps to differentiate between conformations like alpha DNA, beta DNA, or zeta DNA. That is A, B, and Z DNA forms, and also monitors ligand binding. Now the next is fun in pharmaceutical analysis as well. CD plays a crucial role in the pharmaceutical industry for chiral purity, analysis of drug compounds, and investigating drug target interactions. It helps in understanding how drugs binds to their target molecules. Next, now I've got a few case studies, sort of examples. These include first is protein folding studies, and in which CD can monitor structural changes during thermal denaturation. It provides insights into folding pathways and the stability. Second, there's drug binding to DNA, where changes in CD spectrum can reveal how drugs interact with DNA. I've attached the links and the papers in the reference slide. See, Next comes the advantages. Now, there are many advantages to using CD spectroscopy. Some of them like rapid and sensitive. It is rapid and it requires minimum sample preparation. It is capable of detecting even subtle changes in structure. The second advantage is that it is non-destructive. It preserves the integrity of the sample and allows for further analysis or experimentation without making a new sample. Third one, it is versatile. It is applicable to a wide range of chiral molecules. And since we are using polarized light, and it is also falls into UV visible spectrum, thus we can use it for a wide range of this chiral molecules. And these include biomolecules such as proteins, nucleic acids, and small organic molecules as well. Next is the limitations. The limitations, they require, the main limitation is that they require an optically active sample. It makes it unsuitable for achiral molecules or molecules where their mirror images are can be superimposed on each other. The second thing is signal overlap. In complex mixtures, CD signals from different molecules can overlap, making it difficult to interpret the spectra. You can get like mixed peaks or a very wide peak and all of those things because there are complex mixtures involved. So it is very hard to then segregate them. Third one is structural resolution. CD spectroscopy provides limited structural resolution compared to techniques like X-ray crystallography or NMR, which can provide detailed atomic structures. CD spectroscopy, it is used to differentiate products on the basis of their spin that is associated with those molecules, and thus we cannot get like a very detailed atom by atom structure of the molecules involved. Now let's see how CD spectroscopy compares with other techniques. Compared to other techniques like NMR or X-ray crystallography or even IR spectroscopy. It is very fast and it is more straightforward, but it provides less detailed structural information. It often complements these methods. Like we can use CD spectroscopy in conjunction with these methods, and then you can get the complete picture of the molecule that is involved. As we know, NMR, it provides a detailed atomic level structure information, but is limited by sample size and sensitivity. Also, it is very costly. Second is IR spectroscopy. It reveals vibrational modes of molecules, providing insights into functional groups and molecular structure. As we saw, it involves all everything about the bonds of the molecules and all those things. The next thing is X-ray crystallography. X-ray crystallography offers high resolution structures but requires crystallizing the molecule, which is challenging, especially for biomolecules. So now we have seen the basics of CD, the circular dichroism spectroscopy. So what are the future prospects for CD spectroscopy? First, there are advancements in vibrational CD and integration with computational tools. These look promising to enhance the capabilities of CD spectroscopy. It can make it even more powerful for structural analysis. Now, VCD is a promising technique as we know for analyzing very small molecules, offering insights into their absolute configuration and stereochemistry. We can combine it with computational modeling, and it allows for more accurate structural predictions and interpretation of spectra. As for the applications, future applications, advancement in CD spectroscopy are expanding its applications in fields like biophysics, drug development, and material science. So now let me summarize the entire CD spectroscopy once. Summarize it, CD spectroscopy, it is a valuable tool for studying chiral molecules, offering insights into their structure and their interactions. Its applications in biology and pharmaceuticals, it highlights the importance in research and the industry. Now going forward, it has got a very bright future. Here are some of the references that I used. It includes some two YouTube videos as well. I've used a research website for taking out the data, and also it took help of some books. And finally, I'd like to end it. So thank you for listening to this presentation.